I would like to start by thanking the organizer for inviting me and giving me a chance to attend this great conference. So indeed, I will talk about, I will continue with the atomic chains on a superconductor and the work that we did in Princeton. So the work I'm presenting is done in a group of Professor Ali Yazdani, who's doing an STM, as most of the people here, together with Ilya Drozdov, Sang-Jun Jeon, and Jean-Pil Seo. So we also had great theoretical help from Professor Ander Bernevig and his postdoc Jian Li, as well as help from Professor Alan McDonald and Hua Chen, who did the DFT calculations for us. So before I dive in any experimental results, I would like to quickly repeat this recipe that Leonid gave in the last talk, and which describes how do you get the topological band structure from the normal ingredients like superconductivity, spin-orbit coupling, and magnetism. So if you start with a 1D electron band, for purpose of this exercise, it's just assumed to be a parabolic band. It's doubly degenerated due to spin. So now if you induce spin-orbit coupling in this system, the spin up and spin down bands split in momentum. And now, if you start adding magnetic field in a particular direction, which is orthogonal to the spin-orbit direction, you start opening a gap on this band structure. And the more field you apply, the bigger the gap is. And the next thing which you have to take into account is the position of the Fermi level. So taking into account this kind of a band structure and the position of the Fermi level, you can have three situations. You can have the situation that the Fermi level crosses both bands, that it basically crosses one band and touches the other, or it just crosses one band and doesn't touch the other band. And in some sense, these two situations on the left-hand side and the right-hand side are topologically different, because you have, in this case, you have even number of crossings of your Fermi level to your number of bands, and in the other case, you have odd number of crossings. And when you add a superconductivity to this picture, nothing essentially changes. So what you have is, so what you have when you add superconductivity, you have twice as many bands. This is just because of electron-hole symmetry. So that's why you have this cyan and this purple band. But basically, and the other thing which superconductivity induces is a gap. But as you go from this situation with this type of bands, where you have crossing at k equals 0, this crossing remains. And what happens if you go beyond this picture, you will have some kind of a band inversion. And this is what we call the topological superconductivity, as in contrast to like a normal superconductivity, usual superconductivity. And now, if you would have, imagine that you have a 1D superconductor, which is in part topological and in part trivial, and this boundary between the topological and the trivial superconductor, you will have Majorana edge state, which you can just simply imagine as this kind of, at this position when this band structure untwists from a inverted to non-inverted structure. And this is proposed, this way of engineering topological states was proposed back in 2010, actually for semiconductor superconductor structures. And one of the realizations of this proposal was done actually in Delft, in a group of Professor Leon Kohenhoven, where he uses these semiconductors, indium antimonate nanowires, coupled to a superconductor on one hand side, and then he used a whole bunch of gates underneath this dielectric to actually tune the chemical potential and tune the density of states in the wire. And then he uses a normal electrode to inject electrons and probe the spectrum of such a device. And what they found is this characteristic zero bias peak, which corresponds to that there is some increase of density of states at zero energy for particular applied field and basically for the field and the gate voltage applied on the gate. And this kind of experiment was repeated in other labs as well, and with quite similar results. So one of the disadvantages of this approach is actually hard to probe locally this type of structure, because if you imagine you have like a wire, and then you have on top of that you have a superconductor, and people doing STM know that if you do a lot of processing of such devices, you end up with a pretty dirty system which you cannot probe. So what we were trying to think of is how to actually make a similar system in a cleaner setting, something which would be suitable for local probes. And then, okay, Leonid did an extensive review of this, but I will just quickly repeat. So basically, if you put a classical spin on a superconductor, what you will end up is having this in-gap state coming from basically magnetic interaction of this classical spin with the underlying superconducting condensate. And you can actually image these states if you put a single atom on a surface of a superconductor, and you fix your you fix your bias under the value of the gap of the superconductor. You will see that in the proximity of your impurity of your magnetic atom, you will have some finite density of states. And if you go far away from the superconductor, you will have that basically the density of states is suppressed. So now you can imagine that you can realize the same situation as in semiconductor wires. Basically, if you have a chain of magnetic atoms which is ferromagnetically coupled, and you have a superconductor with a strong spin-orbit coupling. Basically, in this situation, you can have the case where inside of this chain you have this inverted band structure, while outside of the chain you have non-inverted band structure, and you can expect Majorana fermions to occur at this interface, at the boundary. As Leonid said, that this is equivalent to having a spin spiral. And actually, in the beginning, we were discussing this in the context of spin spiral just because there were experimental evidence that spirals can be achieved in a very similar system of iron on iridium, which was reported by Wiesendenger's group. And then, okay, so this is just a quick slide to basically give you some overview of various groups who did investigate similar situation where you can have either spin-orbit coupling combined with the magnetism, or just some kind of non-uniform magnetism in space, which can give you this basically topological band structure in the end. And one important thing to also to mention is that I gave you this cartoon in a case where you have one band, but this actually can work if you have many bands in your system, as long as the number of crossings from the Fermi level is odd. So this is just a very cartoonish picture of having 5 bands corresponding to iron, which is actually not really correct if you looked carefully at Leonid's talk. But it just illustrates the fact that if you have 5 bands, you can still have this situation where you're in a topological regime. And it happens in a wide range of parameters where your distance between the bands is big compared to the basically to the level of the Fermi level. Okay, so now before I switch to experiment, I would just use one slide to kind of advertise this machine that we made the experiments in, and it's a system which can go to 1.4 Kelvin. And particular feature of this system, which enabled many of these experiments, is that it can actually host 2 sample holders at the same time. So for the STM experts, they will appreciate the fact that, for example, if you have one sample with like superconducting substrate and the other sample with like, for example, just plain copper, and your tip becomes superconducting, you can go to a copper side and clean the tip or prepare it in a normal state again. And it's also very kind of a nice kind of feature if you want to do spin-polarized measurements.
So with what precision can you then get back to your other sample? Do you imagine you have a chain there? Can you find that chain again?
No. It's very simple answer, no. No, the idea is that you measure on the chains for some time, and nominally you start with a normal tip, with a nice clean normal tip, and if you, by the time you measure 10th chain, your tip is superconducting, and then you have to go back and clean it again. Okay, so what are the experimental requirements for getting this system to work? At least these are the minimum requirements. So you need to have atomically flat superconducting substrate. You need to have these magnetic atoms arranged in a chain geometry. And okay, the other important thing is that you have to have some kind of spin-orbit coupling or spin texture in this system. So what we use is lead substrate. And here is an STM topographic image of lead 110, which we used here. And the advantage of the lead is that you can prepare it in a very clean way. So you can actually clean the surface very well. And what you see here is are atomic steps of lead. And if you even zoom in, you can actually resolve individual atoms. And for this experiment, we use particular surface of lead, 110, which has this property that the distance between the atoms in one direction is different than in the other direction. So you have anisotropy on the surface, which will be important in a few slides. And then, just for the sake of testing the lead, you can actually park your tip anywhere on the sample and actually take a spectrum and see that it fits nicely with the superconducting gap, which you expect from lead, and the temperature of your setup. So now, if you actually evaporate iron atoms onto this surface at room temperature, and they retake this image, you will have some kind of, in addition to nice flat surfaces, nice flat terraces, you will have actually some kind of clusters of iron. But not all clusters are the same. So you will see some of the clusters are a little bit more elongated. And if you zoom in, you will actually find that there are sections of these clusters which make straight chains. And in the rest of the talk, I'll just focus on these kind of sections of which I call them clean segments. If you now, so this is another 3D rendering of the same structure. So you see, so now you see that this anisotropy of the substrate, underlying substrate, and you can actually see that the chains are growing in these rows of lead, which are formed by this anisotropy of the 110 crystal. And now we can take a topography of various sections, and first thing which you notice that okay, these chains are 2 angstroms high, but what you also notice that there are some corrugation on the chain, which means that the iron atoms do not fit perfectly in the lead matrix, so that there is some kind of a corrugation forming. And when we saw this in the first time, we were like very worried and confused. So we asked our friends who are doing DFT whether they can basically come up with a structure which actually reproduces this, and whether can they help us with kind of figuring out what the structure of the chain is. And basically this is what we got back. So the proposed structure of the chain is that it's actually, well, on this picture, 2 atoms high. So what you end up with is having this zigzag structure which reproduces well basically all the feature observed in the topography. So you have this 2-atom high, and then 1 atom, and 2 atoms, and 1 atom, and basically the distance between these atoms here is something which is experimentally measured to be 4.2 angstroms. Yes?
So how much does that structure depend on the width of the cell that you use for DFT?
It's a good question. I am not entirely sure how much it depends, but this width of the cell was chosen by basically this corrugation. So there is a 2.4 to 2.1 basically big corrugation which is observed on the chain, which we gave them as an input, and then they reproduce this small corrugation. So that's the way how the DFT was done.
Okay, and I assume that doubling that would be not computationally reasonable?
Copying that.
Doubling.
I mean, okay, doubling.
The length of the cell to see if that periodicity comes back in. I'm guessing that's just not going to work.
I don't know. To be honest, I don't know.
I don't think you need that, because if you have 4.2 times 5 gives you like 21, right? And then you got 3.5 times 6 gives you like 21 also, right?
Yeah, so in that sense, yeah, that was the same logic that we were using.
Double the result, it's okay.
Basically, this is the minimum cell where both lead and iron is commensurate. So if you take 4.2 and 3.5, yeah, thank you.
So the small corrugation that comes out of the DFT, does that then confirm the experimentally found small corrugation?
It matches, yes.
It matches.
Yes, yes. And also the height is basically matched in this. And furthermore, so one step beyond, which I'm not sure how much is trustful, is that if you take this structure and use tight binding calculation, you can actually reproduce some density of state. So this is experimental density of states on the chain and on the substrate. So basically you have some peaks in a density of chains which are plus minus approximately half a volt. And these are also reproduced by this using tight binding model based on the structure given by DFT.
Why can't you extract the density of states directly from the DFT?
You can. That's actually a good point. I think so. In order to get other parameters, they use this tight binding model for that reason. So now when we kind of convince ourselves to at least to some extent that we know the structure of the chain, we wanted to get information on the spins, what the spins of the chains are doing, and for that we needed to do spin-polarized measurements. So in this, for this measurements, we used bulk chromium antiferromagnetic tips, which are likely to end up with having some iron atoms on it when we did the actual measurement. And then basically you apply a field in a different direction and you poke your islands and your wires until you have contrast. And what you end up with observing that the conductance on the chain is, okay, modulated, but it basically uniformly changes when you apply positive or negative magnetic field. And if you do this for many different fields, basically you can actually reproduce some hysteresis, which confirms that the chains are ferromagnetic. And I want to stress here that basically we have this hysteresis, which is plus minus 250 milliteslas. And in this kind of experiment, the way how we did it, it's not super clear whether we have a chain which is switching in field or a tip. And for this measurement, we think it's a tip which switched at a quarter of a Tesla. So the next thing which you would like to have is a strong spin-orbit coupling, and Leonid already gave some arguments. I will just repeat them here. So lead is a heavy element, and you expect strong spin orbit just based on general arguments like being like symmetry breaking at the surface, and combining this with the basically large atomic number. Also, it comes out from a DFT calculations, but we actually believe that we can see some signatures of strong spin-orbit coupling just by measuring with a spin-polarized tip on a substrate, where we see this kind of basically reduction of conductance if you apply magnetic field. And this, it's not easy to make one-to-one correspondence, but people can relate this to basically some weak anti-localization measurements where you would expect this kind of behavior for systems with a strong spin-orbit coupling. So now, when we basically have these ingredients in place, we can actually ask ourselves how the states inside of the superconducting gap look like. And for that, we choose a particular nicely looking wire which has two kind of clean segments, and then we can zoom in and try to actually measure the density of states, spatially resolved density of states, as a function of voltage that you use. And I will just show you one of these short movies where basically you are still outside the gap. Now at 1.35 you are becoming in the gap, and this is now all inside the gap. And as you approach zero, you have accumulation, of the state at the chain end. Maybe I should do it again. So let me try to. I wanted to stop at zero, but I missed. Yeah, so basically you have some accumulation of density of states at the chain end. And then you can do this, actually you can try to do this spectrum, just take a point spectrum at different places, and you basically see this, that there is a peak at the chain end, and there are no such pronounced peaks at zero voltage away from the chain end. This is more of the same, where we have different cuts for different energies, and at zero energy there is like this accumulation of the states at the chain end. And now I would typically explain this problem with the localization of the end states, but because Leonid gave us such a nice explanation in the previous talk, I would just point out to his paper, and that there are other papers with similar conclusions. What I want to actually stress, so this is more of the same data, so that if you take a spectrum versus distance, you can actually track all these states which live in the chain, and they basically confirm two things. One is that this zero bias peak is again at the end of the chain, and it's kind of disconnected to some extent to the remaining of the spectrum, and it's very well localized in spatially. So another thing which we can actually ask ourselves, is this something at all related to superconductivity? And is this, maybe this is just some kind of reminiscence of a Kondo physics. And this is something which is, we got this question a lot, and especially people in semiconductor community got this question because they use a different superconductor which they cannot suppress. So here it's very easy to verify whether this origin is related to superconductivity or not by applying small magnetic field where you would suppress superconductivity. So if this is like a Kondo physics should not depend on whether you're in a normal state or a superconducting state. So you could actually, if it's something related to Kondo, it should survive the transition from superconducting to the normal state. And here, if you apply 100 millitesla well above critical field, you actually see that the spectrum is quite boring. There are no states inside of this energy window. So basically, there's nothing of this physics survives above superconducting transition. So with the last few slides, I would actually want to just advertise a little bit what's happened after I left Princeton. So people there are continuing working on these chains. And one of the advancement is that now they can actually measure these chains in a different STM setup where they actually go to 250 millikelvin temperature, which is a factor of 5 improvement in resolution. And now actually they can resolve that the lead has 2 gaps, which is kind of known because it has 2 Fermi surfaces. And if you repeat this experiment of like doing spectroscopy on the chain and in the middle of the chain, they still see at the end of the chain 0 bias peak, which is not present or is largely suppressed in the middle of the chain. But now they are actually resolving all this structure which is inside. And the worrisome thing here is that this gap never goes to 0, which is something which we didn't know whether it's a temperature thing or it's something which is related to just the basing property of these chains. The other thing which they are working on is they are actually trying to kind of increase the coupling to the superconductor by embedding these chains completely in a superconductor. And they are doing this by actually evaporating a lead on top of these chains. And what happens in that case is that basically you still have, at the end of the chain, you still have 0 bias peak. And the background, let's say, conductance away from the chain is heavily reduced. The other thing which was also pointed by Leonid is that you can do this experiments with a superconducting tip, and we actually did it in original work, but not very in a systematic way. And I would also like to point out Katarina Franke's work, which actually repeated the growth of these chains and better spectroscopy at the superconducting tip. With the superconducting tip, but there are also a group in Basel which actually grow these chains and studying with the AFM setup, which can have some advantages in determining the structural properties of the chains. So just to summarize, I show you this growth of magnetic chains on a superconductor and hopefully convince you that they may be interesting systems for studying. And with this, I would like to actually thank you, and I'm ready to answer your questions.